Hello friends, today we are just going to start the application of transport phenomena in understanding various physical concepts. For example, if we consider a cylinder like this and this cylinder is supposed to have been connected with a pipe, and this pipe allows the flow of the gas molecules with certain velocity V, and this gas enters into this cylinder, and after time del t we just stop this particular operation. Then what happens is that when the gas was flowing into this cylinder, the gases were not in thermal equilibrium. Is that right? Now, after this stopcock has been inserted and the gas is allowed to settle down, then it attains a thermal equilibrium. Before, how did it attain the thermal equilibrium? That is the big question. The thermal equilibrium is attained by the transfer of momentum that has been gained due to the rising temperature of the molecules that is entering into the cylinder to other molecules that were there in the cylinder already. They may be at low temperature. Let us consider that situation that the temperature of the molecules in the cylinder is very low. So what happens in this case is that, so when this gas enters into this cylinder and the hot molecules would transfer some physical quantity to this molecules. So the transfer of one physical quantity to another quantity will lead to the phenomena which is called the transport phenomena into this particular application of transport phenomena. So as the momentum is transferred from the hot molecules to the cold molecules, they attain a equilibrium which is called thermal equilibrium. And this transfer of the momentum from one molecule to another molecule will result into a friction. This frictional force actually leads into a formation which is called the viscosity. So we wanted to deal with this viscosity over here. So what is the viscosity formula? dq by dt is equals to eta a du. Eta a du. And over here, what we have is, if we just du, not dt, it should be du dz. So if we consider the h, that was the physical quantity that was used to transfer from one point to another in this kind of system that under consideration. Here h you can assume as is equals to mu. So dh by dz is equals to m du by dz. So now putting this, suppose this is B equation and suppose this is A equation, and if we bring this dt over here, so this transport, the transport per unit time is 1/3 dA dt dH dz lambda n into c. So we will put this thing over here, and we will have this eta a du dz eta a du dz is equals to 1/3 dA n du dz lambda in c. So we can put this elementary area approximately. This can be removed, and du z can also be removed. So what we have, eta is equals to 1/3 in lambda in c, where n is the mass per unit volume, n is the number of molecules per unit volume, and lambda is the mean free path, and c is the velocity of the molecule. There is one small mistake. The m is the mass of the molecule, and lambda is the mean free path, n is the number of molecules per unit volume, and c is the velocity. So our expression for eta is this. Now, as our system, in our system, there is also a transfer of, as there is exchange of momentum between these two particles, and this change in momentum would result in the exchange of thermal energy. Now, the second condition, if we can apply this transport phenomena to the thermal energy, then let's see what happens if we apply this condition to the condition to the thermal energy. Then what happens? Let's see. So we can do it in this way. Suppose this dq by dt again, k a dt by dx. So this is the thermal conductivity equation. So we can put this over here as previously as we have done. K a dt around gives us that z by z is equals to 1/3 a, and dH here, let us assume H is equals to E, that is thermal energy. And we have dA, then we put, it is gone, dH is like dE by dZ lambda in C. So where K is the thermal conductivity. The thermal conductivity. So we can write the value of K as 1/3 dE by dt. D by dt lambda in C. And suppose we will assume E equals to E, the thermal energy is equals to m Cv dt. So dE by dt Cvt. So dE by dt equals to m Cv. So you can write K is equals to 1/3 m Cv lambda m C. So here we can take this thing into account. 1/3 is taken. If you just divide this K by lambda, the K by eta, of this thing. So what do we have over here? We obtained this equation for the thermal conductivity equation using thermal energy. So this is A and suppose this is B. So A divided by B. A divided B. What we have? A divided B. That means we have eta by K, coefficient of viscosity by thermal conductivity is equals to 1/3 mn lambda mc is all there. What we have extra over here is 1 by C is there. So we can write K is equals to eta C, where Cv here is the specific heat at constant volume. So this is a very important relationship and is used for practical purposes in determining if one quantity is given, the other quantity can be determined. This is a very important and interesting relationship obtained in case of a gaseous material being transferred from one point to another, and suppose the conductivity of a gas or the viscosity of the gas is to be known, then if we can measure one, the other can be obtained using this equation. That's all. Thank you.